There are several interpretations of quantum mechanics, and each carries different assumptions about what reality is fundamentally made of. Among the interpretations that are most motivated by theoretical concerns, two of the most influential are the Copenhagen interpretation and the many worlds interpretation, MWI. In the Copenhagen interpretation, quantum particles like electrons or photons don't have definite properties, such as position, momentum, or spin, before they're measured. Instead, the particle exists in a superposition, which means it holds all possible values at once. It's only when a measurement is made that one specific outcome becomes real. According to this view, physical properties aren't objectively real until they're observed. Reality emerges through measurement, suggesting that observation or consciousness plays a key role in determining what actually exists. This has led some to associate the Copenhagen view with idealism, the philosophical position that mind or perception is central to reality. The many worlds interpretation takes a very different approach. It claims that all possible outcomes of a quantum event happen, but in different parallel branches of the universe. The wave function never collapses. Instead, it evolves continuously and deterministically. Every quantum measurement leads to a splitting of the universe, where each branch represents a different outcome. In this view, all branches are equally real, and the observer is simply part of the larger system described by the universal wave function. This interpretation supports a materialist worldview, where reality exists independently of observation, and consciousness is treated as a purely physical process, embedded in the branching multiverse.
In the many worlds interpretation, MWI, the idea that the wave function collapses during a measurement isn't seen as a real physical event. Instead, what seems like collapse is explained through decoherence, a process that happens when a quantum system interacts with its environment and becomes entangled with it. According to MWI, the wave function always evolves smoothly and predictably according to the Schrödinger equation. When a measurement takes place, the entire system, including the observer, the measuring device, and the quantum object, splits into multiple non-communicating branches. Each branch represents a different possible outcome, and in each one, a version of the observer sees a definite result. Decoherence is what makes these branches appear separate and prevents them from interfering with each other. It occurs because the quantum system becomes entangled with its surroundings. As a result, information about the system spreads into the environment in a way that cannot be reversed. The different components of the wave function lose their phase relationships, a property called coherence, making it effectively impossible for the various outcomes to combine or interfere. Crucially, decoherence doesn't choose one outcome over the others. All outcomes still happen, each in its own branch of the multiverse. What decoherence does is make those branches behave independently, which gives the illusion that there is only one result, like we experience in everyday life. So in MWI, measurement doesn't cause a collapse. Instead, it leads to entanglement between the system, the observer, and the environment, naturally dividing reality into many coexisting worlds, each showing one possible result. However, not everything is as it seems. While the many worlds interpretation, MWI, is usually described as materialist and independent of the observer, combining it with integrated information theory, IIT, changes that view. In MWI, decoherence happens when a quantum system becomes entangled with its environment, leading to separate, non-interacting branches of reality. But IIT sees entanglement differently, as a sign of integrated information, which is IIT's main requirement for consciousness. As neuroscientist Giulio Tononi puts it in his paper, Consciousness as Integrated Information, a Provisional Manifesto, in footnote 14, quantum entanglement and integrated information, to the extent that one cannot perturb two elements independently, they are informationally one. In other words, when two systems are entangled, they are not just physically connected, they are also informationally unified, and according to IIT, that means they form a single conscious experience. From this, we can conclude something surprising. Consciousness itself causes decoherence. Each quantum branch doesn't just represent a different physical outcome. It represents a different conscious experience, a unique perspective of some observer. This idea aligns closely with the many minds interpretation, MMI. MMI originally suggested that it's not the universe that splits, but the mind. Each observer's consciousness divides during quantum measurements. By combining MWI with IIT, we essentially arrive at the same conclusion. Each branch of the wave function corresponds to a new conscious mind, defined by its own structure of integrated information. So when MWI is viewed through the lens of IIT, it reduces to MMI.
Some may try to avoid the conclusion that consciousness causes decoherence by simply rejecting integrated information theory, IIT. But there's a surprising twist. The many worlds interpretation, MWI, itself puts strong constraints on what kinds of theories of consciousness can make sense within its framework. In MWI, decoherence happens when a quantum system becomes entangled with its environment through interaction. This entanglement is what leads to branching, each branch representing a different measurement outcome. Now, to reach IIT's idea that entanglement equals consciousness, we only need to assume one thing, that minds are part of the natural world, and therefore quantum mechanics applies to them just like it does to everything else. If that's true, then minds, like any other part of the environment, can interact with physical systems, and so they can become entangled with them. Minds should be able to interact just like a detector, a photon, or an atom. But here's where things get interesting. Minds never interact with the outside world directly. Instead, the mind only interacts with its own perceptions, its internal experiences of the world. So, if the mind becomes entangled, it's not with the external object, but with the perception of it. That brings us to a crucial choice. Are perceptions part of science or not? If they are, and we treat them as real elements within quantum mechanics, then they too can become entangled. And in this case, the entanglement would be between a mind and a perception. Both are elements of subjective experience, components of consciousness itself. This means the entangled system, in this case, is not made of matter interacting with matter. It's made entirely of consciousness interacting with itself. Still, entanglement in quantum mechanics is not vague. It's a precise mathematical concept with well-defined properties. Those properties don't change based on what's entangled, whether it's particles, fields, devices, or minds. So, if entanglement equals consciousness in one specific case, as with a mind and a perception, and entanglement is always defined in the same way, then entanglement must be identical with consciousness in general. And that is exactly what IIT proposes. Consciousness is quantum integrated information, which in this context is another way of describing entanglement. Therefore, IIT logically follows from MWI. But since MWI plus IIT becomes MMI, it follows that MWI ultimately reduces to the many minds interpretation.
However, this isn't the end of the story. The many worlds interpretation, MWI, includes deeper complexities that push the theory even further. To see this, we need to look at one of MWI's most important challenges, something known as the preferred basis problem, and how it reveals a major issue that MWI must resolve. The preferred basis problem points to a serious inconsistency in MWI. In this interpretation, the wave function is usually viewed as a superposition of many classical worlds, where particles follow definite paths through space and time. After decoherence, each branch of the wave function corresponds to one of these classical outcomes. In this view, each observer exists entirely within one of these branches, experiencing a single classical version of reality. But here's the problem. If every observer is confined to just one classical branch, then everything within that branch behaves classically. That would mean there's no access to the full wave function from inside any branch. No observer should ever see signs of superposition, interference, or any other truly quantum behavior. And yet we do. We've run double-slit experiments, we're building quantum computers, and we observe interference patterns that directly show the presence of quantum effects. So how is that possible? This creates a paradox. If MWI is right, and reality is made of branching classical worlds, then how did any observer in any branch ever come to discover quantum mechanics in the first place? If the wave function is only the sum of all classical branches, and not directly present in any single one, then it should be invisible from within. But clearly we do observe the wave function and its consequences.
In this deeper form, the preferred basis problem challenges the internal consistency of MWI. It forces us to ask, how can the mathematical structure of quantum mechanics be known from inside a world that appears purely classical? Until that question is answered, MWI remains incomplete. Recently, however, there has been a surprising solution to the preferred basis problem. Physicists have discovered that spacetime itself emerges from the quantum states described by the wave function. This changes how we think about what's real in any given branch of the many worlds interpretation. In his book, Something Deeply Hidden, physicist Sean Carroll addresses the preferred basis problem using the well-known Schrodinger's cat example. He explains, what's special about the awake-asleep basis, in other words, is that the individual states describe well-defined configurations in space, and space is the quantity with respect to which physical interactions are local. A particle can bump into a cat if the particle and the cat come into physical contact. The two parts of the cat wave function, awake and asleep, come into contact with different particles in the environment and therefore branch into different worlds. He continues, this is the basic answer to the question of why we see the particular worlds that we do. The preferred basis states are those that describe coherent objects in space because such objects interact consistently with their environments. These are often called pointer states, as they are the states in which the pointer of a macroscopic measuring device will indicate a definite value rather than being in a superposition. The pointer basis is where a well-behaved classical approximation makes sense, and therefore it's that kind of basis that defines emergent worlds. In simpler terms, the reason we experience particular branches as real worlds is because they are built from coherent structures in space, like cats, particles, and measuring devices that interact locally with their environments. These stable configurations are known as pointer states, and they define the kinds of classical worlds we experience. The key idea here is that spacetime itself emerges from the wave function, so we shouldn't expect to see the wave function within any one universe or branch. Instead, each spacetime universe is a structure that forms out of the wave function. This explains why, from within a branch, we don't directly observe the wave function. It's not part of our experience because it's what gives rise to our experience in the first place. Still, even though we don't directly perceive the wave function, it remains the fundamental structure that determines the behavior of particles in space-time. The classical trajectories we observe in our branch are shaped by the deeper underlying quantum state that contains all branches. However, using emergent spacetime to solve the preferred basis problem introduces deeper consequences for the many worlds interpretation, MWI, consequences that aren't immediately obvious. The idea that spacetime can emerge from the wave function is rooted in a larger proposal within theoretical physics, that spacetime itself arises from patterns of quantum entanglement. This idea shows up in several advanced frameworks, such as tensor networks in the ADS-CFT correspondence and the ER equals EPR conjecture, which suggests that wormholes, Einstein-Rosen bridges, are equivalent to entangled particles, Einstein-Podolsky-Rosen pairs. If we take this idea seriously, then solving the preferred basis problem in MWI doesn't just involve decoherence. It also requires that entanglement plays an active role in producing spacetime structure. In other words, for us to experience classical-looking worlds with local particles, stable geometry, and causality, the underlying entanglement structure in Hilbert space must be what creates those features of reality. So, if MWI is true, and if solving its internal problems depends on emergent spacetime, then entanglement must be the driving force behind both the branching of worlds and the structure of space and time. This leads to a powerful conclusion. Everything we observe, space, time, cause and effect, and measurement outcomes, emerges from patterns of entanglement within the wave function. In this view, MWI isn't just a theory of branching universes. It becomes a theory where the entanglement structure of the quantum state defines the very nature of reality. As we've seen, the many worlds interpretation, MWI, leads to the conclusion that entanglement is identical to consciousness. This isn't an extra assumption, it's a direct result of how MWI explains decoherence. In MWI, decoherence occurs through entanglement with the environment, and since minds are part of the environment, they too can cause decoherence. That means minds can become entangled with quantum systems in the same way measuring devices or particles do. This matches exactly what integrated information theory, IIT, proposes, that consciousness is integrated information, and in the quantum context, integrated information is entanglement. So MWI and IIT independently arrive at the same conclusion. Entanglement is the structure of consciousness. But MWI also needs spacetime to emerge from entanglement in order to solve the preferred basis problem. In this view, classical reality, the world of objects, locations, and motion, arises from entanglement patterns in the larger mathematical structure known as Hilbert space. Now combine those two ideas. If entanglement is consciousness and space-time emerges from entanglement, then it follows directly that space-time emerges from consciousness. And that is the central thesis of quantum idealism. So if MWI is true, and its consistency requires entanglement to generate both conscious observers and space-time itself, then quantum idealism logically follows. In other words, if MWI is correct, then so is quantum idealism. But the many worlds interpretation actually goes even further than supporting quantum idealism. MWI isn't just about isolated measurements or local branches of reality. At its core, it entails a universal wave function, a single quantum state that describes the entire universe. That's what makes the many worlds possible. They all exist as components of one overarching superposition. Without a universal wave function, the very idea of parallel universes doesn't hold together. Now, think about what entanglement really means. Two or more particles are said to be entangled when they share the same wave function. But if everything in the universe is described by one wave function, then all particles are entangled. This isn't just partial or limited entanglement, it's complete universal entanglement. Earlier, we saw that MWI implies that entanglement is identical to consciousness, especially when combined with integrated information theory, IIT. So, if the entire universe is entangled, and entanglement is consciousness, then it logically follows that the universe itself is the manifestation of a single unified consciousness. This leads to something even deeper than quantum idealism. It becomes what we can call cosmic quantum idealism. The idea that all of space-time and all the parallel branches of the multiverse emerge from one cosmic mind. Or, as physicist Max Planck once put it, this is the mind which is the matrix of all matter. So, if MWI is true, then not only does space-time emerge from consciousness, but every universe within the multiverse arises from a single, all-encompassing cosmic consciousness. Some people may feel uneasy with the conclusion that space-time emerges from consciousness. To avoid it, they might turn to other interpretations of quantum mechanics, hoping for a different outcome. But here's the reality. The theory-motivated interpretations, those that arise naturally from the mathematical structure of quantum mechanics itself, generally fall into two main categories. The first group includes Copenhagen-style interpretations, such as the original Copenhagen interpretation, along with its modern variants like relational quantum mechanics and quantum Bayesianism. These approaches all focus on the relational nature of measurement, where physical outcomes only make sense relative to an observer. It was from this idea that the concept of consciousness causing wave function collapse first emerged. As a result, these interpretations are inherently idealistic in their understanding of reality. They treat experience or observation as fundamental to what exists. The second major approach is the many worlds interpretation. This view removes the idea of collapse altogether, but as we've seen, it still leads, through decoherence, entanglement, and emergent spacetime, to the conclusion that consciousness and entanglement are one and the same, and that spacetime itself emerges from consciousness. There are other interpretations, such as pilot wave theory, objective collapse models, or superdeterminism, but these tend to rely on speculative or non-standard physics. Many of them are also ad hoc, introducing many extra assumptions or mechanisms that aren't part of the core theory, often without strong theoretical motivation. So, when we focus only on the mainstream theory-driven interpretations, those grounded firmly in the formalism of quantum mechanics, both major branches, whether Copenhagen type or many worlds, lead to the same philosophical conclusion. Orthodox quantum mechanics implies idealism. The only remaining way to reject the conclusion that the universe is idealistic is to deny that minds have any real independent existence. This would mean either claiming that minds don't exist at all, which is clearly absurd, or insisting that they are emergent from physical processes. In that view, minds aren't actual components of the environment, but mere side effects with no real ontological status. But this strategy fails for a deeper reason. It would require that first-person consciousness, our inner subjective experience, somehow arises entirely from third-person objective processes, without any logical or explanatory connection between the two. That isn't science, it's magic. In fact, it's no better than old-fashioned substance dualism, which has long been criticized for its interaction problem. It posits two fundamentally different kinds of reality, mind and matter, but does not allow for even the possibility of an explanation for how they interact. In both substance dualism and emergentism, consciousness plays a central role in our experience of reality, yet is not given any solid place within the theory being used to describe the world. This makes for a deeply inconsistent worldview. If we want to be truly scientific, not magical, we have to treat minds as real, physical participants in the environment. Minds interact, they entangle, and they evolve just like other physical systems. And if that's true, then at the quantum level, they must be identical with entanglement itself. And that brings us once again to the central conclusion. If minds are real and quantum mechanics is true, then the universe is idealistic.
If you like this video, subscribe and support me on Patreon. And don't forget to check out the books in my Alaris novel series, Alaris, The Lances of Light, and Alaris, The Pearl of Heaven, on Amazon Kindle in the description below. You can find us on Facebook as well, at Idealism and Science versus Atheism.